In previous videos we've looked at using Pythagoras Theorem, the trig ratios, the sine and the cosine rule for finding missing lengths and angles in right angle and non-right angle triangles. In this video we're going to look at some problems in context and use the different skills to solve them. Let's start off with the first question. It says to calculate the height of a church tower, a surveyor measures the angle of elevation of the top of a tower from 2 points 50 metres apart. The angles are shown in the diagram. In part A we need to calculate the distance BC, and in part B it says hence calculate the height of the tower CD. Let's just go ahead and draw a triangle on this particular picture. So what we're after now is this length just here, and that is the length BC. I've got now a length of a triangle. I've got one known angle in 40 degrees, but I can find the other two. We know that angles on a straight line sum to 180, so this angle right here is going to be 133 degrees. That's the angle just here. Angles in a triangle sum to 180 degrees, so I've got 173 in total. This one is going to be 7. So what we're looking for now is the length of C to B. We can see that we're missing a length, which I'm going to call X. You can of course call that C to B. I've got one known side and I've got all three known angles. I'm going to use the sine rule here, and we can say that in general A over sine A is equal to B over sine B, as we've seen in previous videos. So I'm going to write this, we can either write it as CB or X. I'm going to write that X over the sine of 40 degrees will be equal now to 50, which is the opposite to the 7, 50 over the sine of 7 degrees. So all I'm going to do is multiply it by the sine of 40. So X will be equal to 50 lots of the sine of 40 divided by the sine of 7 degrees. We're simply going to put this through a calculator now and find this length, which is B to C, or the value of X. So in our calculator, shift mode 3, just to check that you're in degrees. You'll have a little d here. And what we're going to have is 50 lots of the sine of 40 degrees divided by now the sine of 7 degrees. So if we do that, we end up now with 263.7. So X is going to be equal to 263.7. That's meters, and that's given to one decimal place. So I've simply used the sine rule. If you want a more explicit picture of that triangle and taking out the information that we need, it's going to look something like this. So what we have now is the following. We're going to have this one, which is going to be 50. We've got 7 degrees just here. We want to find this length right here, which is X, and we have the 40 degrees here. So I've simply now said that X over the sine of 40 must be equal to 50 over the sine of 7, with a basic application now of the sine rule. Let's go ahead and do the next bit. We need to calculate the height of the tower CD, which is this length just here. I can go back to my trig ratios here. What I'm going to do is draw up a different triangle here. I've got this angle right here. This is going to be 47 degrees. We've got now this right angle. Remember, the wall of the church tower and the floor are going to be perpendicular. And we found this length right here, 263 point dot 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 dot, which I could, if I wanted, store in the calculator. So we've got 263.7 and so on and so forth. Shift store A. Just in case I make a mistake, I can bring that back by pressing recall A at any time. So recall A will bring that value back. So what we're looking for now is this height just here. So this is going to be C, this is going to be D, and we have the angle here. If we consider now, we have the hypotenuse, we want the opposite, which is CD, so we can go back to our trig ratios. We saw using our trig ratios, and I'll just draw this up, we use the SOH triangle. So if I just write this up now, Let's put this on. You don't have to do this. I appreciate some people don't, but it is an option for you. So I've got the OMH, so this is going to be sine, so we can put in S, we can put O, we can put H. I want the opposite, finger over opposite, and it's going to be the hypotenuse multiplied by the sine of the angle. So 263 dot 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 multiplied by the sine of 47 degrees. And that will give me now the height CD. So we can write that CD, and we're going to grab this value up, so multiplied now by the sine of 47 degrees. So let's just put this in, and that is going to give us on here 192.9, and that is in meters, correct to one decimal place. So 192.9 meters, and that's given to 1 dp. We're not given a level of accuracy, so I'm going to give my answer now to 1 decimal place. So we got a multi-step problem using first the sine rule and then trig ratios. In this one, we're asked to calculate the length of KB and then calculate the size of the angle NKB. So if we look here, we've got an enclosed angle and 2 given sides. In this case, if we want to find KB, we would use the cosine rule. So I'm going to find this length here. I've got now 2 known sides and an enclosed angle. So let's go ahead and calculate now the length of KB. If you like, you can put on there that this one is going to be A, and this one is going to be little a, this one is going to be little b, and this one is little c. The cosine rule says now that a squared is equal to b squared plus c squared minus 2bc cos a. So if we just plug in these values, a is going to be the square root now of b squared. That's going to be 14 squared plus c squared, which is 21 squared, minus 2 lots of b, which is 14, multiplied by c, which is 21, multiplied by the cosine of 81 degrees. So let's go ahead and find that value. So if we take now the square root of 14 squared plus 21 squared minus 2 lots now, so 2 times by 14 times by 21 times by, let's just put in 14 rather than 4, times by 14 times by the cosine, and you can put this in how you like, you can use brackets or multiplication, cosine of 81 degrees. So that gives me 23.34, so let's put this in here. A is going to be equal to 23.34 dot dot dot. If we want to give this now to, let's give this to 1 decimal place, we can say 23.3 centimeters, and that is to 1 dp. That seems reasonable given the dimensions that we've got. Let's just check that I've got all of that in there. 14 squared, 21 squared, minus 2bc, and then we're going to have now cos of 81 degrees. I'm going to store this in the calculator. Let's just get that answer. So shift store A. So that's now in the calculator. So if I want to bring it back, there it is. We now need to find the size of the angle NKB. This is the angle just here. And what I'm going to do is draw a triangle below. So with my triangle, what we're going to have is the following. Let's just put this on. It's going to look something like this. So we know that we now have this angle right here. This angle is going to be 81. We now have the 23 dot 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 stored in the calculator. I've got this length right here, and I want this angle just here. This is the angle NKB. So we want to find a missing angle. We've got one angle and 2 given lengths, so we're going to use the sine rule. We saw that for an angle we could write sine A over A is equal to the sine of B over B. So in my case I'm going to write that sine theta over the opposite, which is 21, will be equal to the sine of 81 over my answer of 23 point dot 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 that's stored in the calculator. So we can write now that sine theta is going to be 21 sine of 81 degrees over the 23 point dot 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 in the calculator. So let's go ahead now and get a value for sine theta. So I'm going to have on here now 21, and then we'll have the sine of 81 degrees, and I'm going to divide that by the value of a, recall a, so that gives me 0.888 and so on and so forth. So that is now 0.888 dot 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 dot. So we need to take the inverse sine of both sides of the equation. We've seen this in the tutorial, and that will give us now our value for the angle. So let's go ahead and do that. Let's do that. So we'll do now inverse sine, shift sine of that answer, and we end up now with 62.67. So I'm going to say now that that is 62, so writing this in, 62.67 will be 62.7, let's just check I'm rounding this correctly, 62.7 degrees to 1 dp. So that now gives us the angle that we want. Just here, we've gone ahead and solved it. So I've used one application of the cosine rule to find a missing length, and then the sine rule to find a missing angle. In this question, we're told Nottingham is 40 kilometres due north of Leicester. So here's Leicester, here's Nottingham. Swadlincote is 32 kilometres from Leicester and 35 kilometres from Nottingham. We're asked to calculate the bearing of Swadlincote from Leicester. So what we're looking for then, the bearing now is going to be round the outside. We measure bearings from north, we measure clockwise, and we measure round the outside. What I'm going to do instead is the following. I'm going to find this angle right here, and I'm going to subtract that. I'm going to call this theta, and I'm going to say that the bearing is going to be 360 minus theta. So just jotting this in. So bearing will be equal to 360 minus the value of theta. The reason why I'm choosing this is because I can use the cosine rule. So if we look now, we can say that we have a triangle with 3 given sides. If we've got a triangle with 3 given sides, we can go ahead and find the angle. So what I'm going to do is just label these up. What we'll have is this. I will call this one A, so this is going to be big A. This is going to be now little a, this will be B, and this will be C. In the tutorial on the cosine rule, we saw that the cosine rule could either be written as a squared is equal to b squared plus c squared minus 2bc cos a, or if we wanted to rearrange it, cos a was equal to b squared plus c squared minus a squared over 2bc. So that's what I'm going to do here. I'm going to find this angle, and I can say now the following. I can write that cos theta is going to be equal to b squared, which is 32 squared. Then we're going to have plus c squared, which is 40 squared, minus a squared, which is 35 squared, and that's all over now 2 lots of b, which is 32, multiplied by c, which is 40. So let's get a value for cos theta. So let's do that. So if we do that, we're going to have now 32 squared, plus now the 40 squared, minus the 35 squared, and we're going to divide this now by 2 times by 32 times by 40, and that gives us that cos theta is 0.54 and so on and so forth. So cos theta is equal to 0.54 dot dot dot. So we need to take the inverse cosine, so theta will be equal to the inverse cosine of the 0.54 dot 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 that we have in the calculator. So we're in degrees mode, shift cos, it's the inverse cosine, cos to the minus 1, or arc cos. That's going to give us now 56.87, so theta is equal to 56.87 dot dot dot. Therefore the bearing, so if we just write this, the bearing will be equal now to 360 minus this 56.87, and we can do that in the calculator. So I'm just going to store this in case I make an error. Shift store A, 360 minus our answer, and we get 303 degrees. So 303 degrees, and that is correct to the nearest degree. So nearest degree. So I've gone ahead and found that by simply applying the cosine rule to find this angle here, and then considered now that if I have a bearing, bearings are measured from north, we have a north line, then measured round the outside clockwise, 3 figures, and we can see that that is simply 360 minus the value of theta. We're told the banks of a river are straight and parallel. So let's just put that on before I forget. These are straight, so that is straight, and that is straight, so these two are parallel. To find the width of a river, 2 points A and B are chosen 50 metres apart. The angles made with the tree at C on the opposite bank are measured as angle CAB, which is 56, and angle CBA, which is 40 degrees. We need to calculate the width of the river. Okay, so with this now, what we can do is use some multi-step, use a multi-step approach. Essentially, what I'm looking for is this distance, so the width. Now, I could put a perpendicular just here, and there are a few different ways around this question. The first thing I'm going to do is just put on a bit of missing information. If we consider now we have 2 of the angles in the triangle, therefore we're going to have this third angle. The sum of angles in a triangle always give us 180, so this is going to give me 96, so this one is going to give me 84. What I'm going to do is choose either this one to find or this one to find, so either AC or CB. So if I look at this and I draw a quick triangle below, what I can do is find either one of these. So quick SketchUp, let's put this on. I'm going to have something that looks a bit like this. So I'm going to be interested now in the 84 degree angle. So this is going to be the 84, so that is 84. This is going to be 50. I'm going to take this angle right here to be 56, and I'm going to call this length CB, let's put this CB, as X. So if I can find this length, I can then go ahead and just use basic trig ratios. So what I'm going to say then is that X over the sine of 56 will be equal now to 50 over the sine of 84 degrees. What I'm essentially looking to do here is get this length right here. I want the perpendicular height. Once I have this length here, I can go ahead and use one of the angles and use basic trig ratios. So X is going to be equal to 50 sine of 56 degrees over the sine of 84. So let's go ahead and find this length X. So if I do that, in the calculator, we're going to have now 50, so let's just put this in, 50 sine of 56, and we're now going to divide that by the sine of 84 degrees. So that's looking what I want from my triangle. Let's just check I've got this in. X over sine 56 is going to be equal now to 50 over sine of 84. So that works out quite nicely. So let's go ahead and find that. So this length right now is going to give me 41.68. So I'm just going to check I've got all that in, that looks okay. So what I'm going to do is draw now another triangle. This triangle here is going to look something like so. So I'm just dropping this perpendicular back in. So if I go ahead and drop that in, what I'm looking for is this distance right here. I've just found the length C to be. So if I put this on, this is going to be the 40 degrees. I'm going to have this length right now, which is the one that I've just found. So this is going to be the 41.6 ... I want this length right here. So if we look at this, this is the hypotenuse, this is going to be the opposite, and I want the opposite. So we know from our triangles SOH, so all I'm going to do is multiply the hypotenuse by the sine of 40 degrees, and that will give me this perpendicular height, or the distance across the river. So we can say now that this is going to be the 41.6 ... multiplied now by the sine of 40 degrees. All I've said, I want the opposite, it's the sine times by the hypotenuse. So sine of the angle multiplied by hypotenuse. So just storing this in, if I make a mistake, we can multiply this now by sine of 40 degrees, and that's going to give 26.8, and that is correct to 1 decimal place. So that's going to be equal to 26.8 meters, and that's 1 dp. So that is the distance across the river. So we've just gone ahead and found that. So one way that you could look at that, plenty of different approaches, but that will certainly do it. one application of the sine rule, and then one application now of basic trig ratios. Remember as well, you can of course use Pythagoras Theorem in certain situations. These are still utterly valid. Just because we've moved on to look at the sine and cosine rule doesn't mean that we don't use them, because quite clearly if we've got a right angle triangle it will be easier to use Pythagoras if we've got two of the known sides. Okay, let's move on to one more. The bearing of a beacon from an aeroplane is 160 degrees or southeast 20. We're told the aeroplane flies due south of 5 kilometers and now finds that the bearing is 135, which is southeast 45. We're asked now what is now the distance of the beacon from the aeroplane. Okay, so quite a tough question here. Let's just sketch something up. I always like to draw these on a grid. You certainly don't have to, but I think it could help. So if I put my north line just here, initially what we're going to have is the beacon, and then we're going to have the aeroplane. So we've got the aeroplane, so let's put this on. The aeroplane is going to be at the origin. So this is one way that we could do it. So the aeroplane is at the origin, and the beacon now is on a bearing of 160. So if I put 160 on, we know that this is going to be 90 just here. 160 is going to be somewhere down here. So let's just put it's going to be somewhere down here. So if I want to, what I can now do is put on some angles. So if we think about this one here, this angle right here, we know is going to be 90. I'm going to put now that the beacon is just here. This angle, if we're on a bearing of 160 degrees, is 70. This angle right here will of course be 20. We're now going to go 5 kilometers south. So if we do that, what I'm going to do is just plot the path 5 kilometers south. So I'm just going to come down here somewhere, and we're told now that the bearing is going to be 135. So if I just put up a line, and again you don't need to do this, but it might help. If I put that just here, what we're going to have now is a bearing, and that bearing is 135. So there's 0, there's 90, and 135 will look something like that. If I put the information up that I've got now, this length right here, from where it started to where it finished, is 5 kilometers. I know that that's 90 degrees, so I've got 135 here. If this is 135 and that's 20, that's going to give me 155 degrees. So if I put on this one right here, 155, we need to add to that now 25 to go ahead and make a triangle. So all I'm going to do is a quick sketch here. Let's just bring this here. So I've got now 5 kilometers. I've got something that looks like this. So let's put on this information. We've got 5 kilometers here. So we know that this is going to be 135. We know that that is going to be 20. That gives me 155. Triangles add up to 180. The angles sum to 180. So this is going to give me on here 25. What we're looking at now is what is now the distance of the beacon from the aeroplane. So the aeroplane is just here, the beacon is just here, and we need this length right here. So what we can do is go ahead and use the sine rule. I'm just going to call this d or x, let's just call it d, that's the distance. So using the sine rule, we can say that a over sine a is equal to b over sine b. So I'm going to say now that d over the sine of, we've got the 20 degrees, will be equal now to 5 over the sine of 25. And this is one way that you could do it. You don't have to do it this way. And there might be a slicker, just thinking about it, there might be a slicker way to do it. But this is certainly going to give us what we require. So all I'm going to do to solve for d is 5 sine of 20 over sine of 25 degrees. So if we put that in the calculator, we know that we're in degrees mode. 5 sine of 20. So 5 sine of 20, and we're going to divide that now by the sine of 25 degrees. And that is going to give me now that d is 4.046. So we'll say that 4.05. That's going to be kilometers, and that is given now to 2 dp. So 2 dp will be our answer. So there we go, 4.05. So that is the distance. So I've gone ahead and used now the sine rule on that particular one. Yeah, I think maybe could it be done any slicker than that? I'm not. I think if we sat down and did it a few times over, we might find an alternative, but that will certainly give us the answer that we want. So there we go, using the sine rule, the cosine rule and the trig ratios to solve problems in context.